Okay, so we've done some work about working out the graph given a particular form of a function, and we've done some work or changing or adapting a form that we're given and turning it into another form. So that's what we've done so far. But if we're looking at, in inverted commas, reality, frequently what happens is that we're presented with an image, not necessarily an image, but data that we've collected or an image that we've received, and we want to model that as a function, because once we've modeled something as a function, we can use that. So, for example, a satellite dish is an example of a parabolic shape. Okay, it's literally a parabola, the shape of a satellite dish. Now, I can't graph that because it would fail the vertical line test. But if I rotated the image, if you could imagine, then I could graph that. Or perhaps, what else have I got? Or perhaps it's a whole set of data that you've collected, and the data you feel fits a parabolic curve or part of a parabolic curve. So you've got this graph picture. And here's a third one. This is a basketball bouncing, and the the shape created by tracing the path of the basketball bounce becomes a parabola. In this case, it's probably also a geometric sequence of parabolas, because it's getting smaller and smaller at each bounce. Okay, so but each from bounce to bounce, it's a parabola, I should say, I suppose. So
it says that that's a myth.
Sorry?
It says that that's
I know. If you look at it more closely, it's really, I'm getting sidetracked, but very, very, very quickly. If you look at it more closely, you'll find that these parabola bounces, which is basically what you'll always learn in physics, is that throwing a ball or bouncing a ball always makes a parabolic shape. It only makes a parabolic shape if you're talking about a genuinely flat surface. As soon as you put it on the Earth, which is a curved surface, it actually is an elliptical shape. So, oh man, now I'm going to do it now, aren't I? Because it's really quick, because it's just the pictures only. So I took, ad block. Hang on. Nope, don't want to do that. So it basically just says, if it's flat Earth, projectiles follow parabolic arcs, but Earth is not flat, and so it actually is more of an elliptical arc. So it's kind of like more like that. But anyway, you know what? I mean, it's a worthwhile, very, very short sort of digression, in that what you'd have to ask yourself is, when will that be important? And it's the same thing in physics, like, certain facts about gravity, for example, and those facts hold true unless you're looking at the quantum scale, in which case they don't hold true, in which case you need to use a different model of physics in order to describe what's happening at a quantum level. But if you fall out of a tree, you will hit the ground because of gravity. You know what I mean? Like, it depends on the scale that you're thinking of. Same with the electron model. What's it called? I can't remember. But the model of the Bohr model, which is not actually what's happening, but it's actually a good enough approximation for what you're doing. So if I'm describing the arc of a ball as I bounce it across a basketball court, parabola is pretty good. But if I'm talking about trying to trace the pathway of a satellite that's going up and down, a parabola is probably no good. Do you know what I mean? So anyway, that's useful for knowing for the hanging change thing. Sometimes, I mean, you know me, I don't say this lightly, but sometimes near enough is good enough. You know? It just depends on the context. Near enough is sometimes good enough. So bouncing ball. So all of these are kind of parabolic shapes, and what we would want to do then is we would want to model them as a function. So what we're going to practice today, very artificially, because it's like using Cartesian plane and all that kind of stuff, we're going to model, if I've got a picture of the graph, then how do I go about working out what the function would be? It's not too bad. You just need to know how to do it. So this is where the notes start. It's good so far, isn't it? I'm going to go through three. For those who have just turned up or turned up since I first spoke, I have been tested. You're safe with me in the room. I've got three examples to go through, and basically, the way you solve these sorts of things, the way you come up with a quadratic function given a graph, is the way you start is by trying to figure out what you've got, and then deciding which form would it be best to try and fit it into. So, example one, quadratic form, general form, vertex form, or intercept form. Which one do you reckon? Let's go straw polling. General form. Vertex form. Intercept form. I don't know, just tell me. That's for the rest of you who didn't put your hand up a second ago. I'm assuming that's what you meant by it. Okay, so basically, if you've got the intercepts, that's probably the easiest thing to figure out. So we start off by writing y is equal to, and we can see that we've got an intercept of -1 at y equals 0. So that means that x plus 1 must be a factor. And we've got x equals 2 at y equals 0 over here, which means x minus 2 must be a factor. And so I've got, x plus 1, x minus 2 as being our quadratic. Is everyone okay with that so far? So far, so good. Except it's not the full story. Why? Yeah, because dilation will affect the graph. Really briefly, I should do this on Desmos, but I can't be bothered. That and that and that, all of those have the same x-intercept, but they are different graphs, right? What makes them different is dilation. If it was a translation, then everything would go up or down, so that's not right. So it's not an up or down. If it was left or right, that wouldn't make sense because the distance is different. What it makes sense is that multiple graphs can be found by dilation. And you'll find that that is more or less almost always what you are trying to do. You're trying to figure out the dilation that goes with it. Okay, so we start with an unknown. Y equals a outside of x plus 1, x minus 2. By the way, working out a will also tell you whether it's a reflection or not. Can you see how example 2 is reflected? So because example 2 is reflected, we're going to get a negative a value, and the negative will tell me it's reflected, and the value of a will tell me it's dilated. Okay? So all we need to do is we need to solve for a. We can't just leave it like that, obviously. So I picked the other point that I've got, which is 0, -4. Can you see that down the bottom there? It's actually the y-intercept. Doesn't have to be. It can be any point along here. But I can't use these 2 points because if I substituted either of these 2 points in, one of these factors would be 0, and then I wouldn't be able to work out what a is. But this point here is 0, -4. So I simply substitute in that point. So instead of y, I have -4. And instead of x, I have 0. And now I can solve because I've got an equation with one unknown, a. So I've got -2a is equal to -4, and therefore a is equal to 2. Is that okay, peoples? Ask questions now or forever hold your peace. I'll wrap up the problem, but this is a stop for anything you want to ask me. Okay, so therefore y equals 2x plus 1, x minus 2. That's enough, unless it says express in general form or in vertex form. I'll just go as far as general form. Now, unlike cubics and other polynomial graphs, remember that quadratics always can be expressed in one of those three forms. Oh, actually, that's not quite true. If there's no x-intercepts, then it can't be expressed in intercept form, of course. But it can always be expressed in general form. It can always be expressed in vertex form. So just for the sake of it, I'll just very quickly do the rest. Now, unfortunately, in English-speaking, westernized world, we tend to work left to right. And so you think 2 times x plus 1 will be the first thing I would do. But in fact, you're actually making your life harder by doing that. And because you've got 3 things multiplied together, you can just multiply the last 2 things first. And it does make your life a little bit easier. I know 2's not that hard, but imagine if it was 7 or something like that. It's much better if you expand the 2 bracketed bits first. So that's going to be x squared. And then I'll just do this in fast format. 1 times x is x, minus 2 times x is minus 2x. X minus 2x is negative x. And then minus 2, which is equal to 2x squared minus 2x minus 4. And that's in general form. GF, that does not mean gluten-free. It is not a gluten-free quadratic. It's probably full of gluten, let's be honest. Okay, any questions? Okay. Example 2. In this case, we don't have the x-intercepts, nor do we need to work them out. We're going to use what form? Hopefully it's pretty obvious. Not really, it's not. Thank you, Zoe. Is that really not obvious to anyone else? What information have you got? You've got the vertex. So it'd be crazy not to use vertex form if you've been given the vertex. You've also been given the y-intercept only because it's easier. It could be any other point. So it's the same format. See if you can get ahead of me if you like. So we start off as y equals a outside of x minus 1 all squared, and then it's up 12 units, so plus 12. There we go. Now, do know, for the astute amongst you, most of you wouldn't pick this up, and I wouldn't expect you to, but for the astute amongst you, note that I'm not using bx minus 1, and therefore having to work out what b is. Ultimately, for a quadratic, it doesn't work for other polynomials, but for a quadratic, a b can always be factored out into our transformation here. So there's never any need to work out what b is when working out the function from the graph. Substituting in the point we know, I've got a y-intercept of 9, which means that the x value is 0. Yep. So 9 is equal to a outside of 0 minus 1 all squared plus 12. So 0 minus 1 is negative 1, which I've then squared to make a. So we've got a plus 12 is equal to 9, and then subtract 12 from both sides to get a equals negative 3. So you've got y equals negative 3, x minus 1 squared plus 12. And as usual, check for understanding, right? I've got a equals negative 3. Does that fit the shape of this graph? Yeah, it's reflected. So that makes it. If you ended up with a equals 3 and you had a graph that looks like this, then you've made a mistake. So go back and fix it. Again, in a textbook situation, your textbook's going to tell you got it wrong, although that's been known to have mistakes, hasn't it? Just a few. But the other thing is, guess what? In an exam, you don't get the answers, you might be shocked to hear. So getting into the habit of mind of going, is my answer reasonable? A equals negative 3, is that reasonable for the graph that I've been given? Is a good thing to do. It's also, yeah, no, I'd say anything more. But yeah, so it's just definitely worth doing. Now, I'll do the same thing. I'll just put it into gluten-free form. So do note that BEDS maths says Brackets, there's nothing to fix in the brackets, so that's as simple as you can get. Exponents, then multiplication, division, addition, subtraction, left to right. Never ever multiply the number outside the bracket inside the bracket while there's a square or a cube or whatever here. Never ever ever. Number one, doesn't work. Number two, you get the wrong answer on me. And number two, big math says you have to deal with powers before you can deal with multiplication. So you would in fact get the wrong answer by multiplying out by -3 first. You should know your perfect squares. So it should be x squared minus 2x plus 1 as the expansion of x minus 1 squared. And that's equal to minus 3x squared plus 6x minus 3 plus 12. And finally, we've got minus 3x squared plus 6x plus 9. And that's it. That's the gluten-free form. Any questions? Moving on. Example 3. Example 3 looks, it's deceptively harder. It kind of looks like as if, well, you've been given, but I'm going to zoom up for tick. You can, it looks like as if it's pretty much the same sort of thing. You've been given a few points. But it's not as easy as it looks, really, because you're not given the vertex and you're not given the x-intercepts. I'm going to pause the video for 1 minute, and I'm going to see whether you can get ahead of me. See if you can get an approach that works. For the sake of the recording, I'll just say that we just discussed a few different ways of doing it. What I would probably do is I would substitute in some of the points I do know. The first thing we do know, I suppose, one thing I have been given straight up is the y-intercept. So, which of the three forms naturally uses the y-intercept as part of its form? The gluten-free form, isn't it? Yeah, the general form. I think I'm calling it the gluten-free form. The general form. Because it's y equals ax squared plus bx plus c. So c is already in the general form. So I can actually just start right off the bat by saying ax squared plus bx plus 1. Because I'm told that's the y-intercept. Anyone start like that? Waggle a paw in the air? Yep. Cool. One person did. So that's a start. We've got 2 unknowns though. But I've also got 2 points. So my other point is minus 1, 0. So I'll start by substituting that in. So y is 0 and x is minus 1. And minus 1 squared is 1. So I've got a minus b plus 1 is what 0 is. So I've got a minus b equals -1. Now I can't do much with that because it's 2 unknowns and a single equation. But I've also got another unknown, and that's minus 2 minus 2. Have I made a mistake yet? I don't think I have. So we've also got this other one as well. So I've got at minus 2, I've got a minus 2 squared plus b minus 2 plus 1, which equals 4a minus 2b equals minus 2. And I might simplify that because I've got a common factor of 2. So I'm going to divide by 2 everywhere. And I get minus 5.
You missed the plus 1.
Thank you. I was probably going to stuff myself up by doing that. So I've got minus 3 is 4a minus 2b. Okay, and that's equation 2. So I've got 2 equations with 2 unknowns. So if there's a solution, guess what technique I can use?
Simultaneous equation.
Simultaneous story time? Yeah, simultaneous equations. So I can go from 1, doesn't matter which one I use, a equals b minus 1 sub into 2. Is that okay? So I've just added b to both sides there in equation 1 to get b minus 1. I've added b to both sides. Okay, and now I can substitute b minus 1 for a. So I can get for negative 3 is equal to 4 multiplied by b minus 1 minus 2b. Now I have an equation with one unknown. Hooray! Now I can figure out what's going on. So I've got 4b minus 4 minus 2b. Add 4 to both sides to get 1, and 4b take 2b is 2b. And so I've got b is equal to 1/2 or 0.5. What do you think? Like I said, this is on. I told you it's harder than it looks, didn't I? Didn't I? I don't think this is hard though, so I'm worried I made a mistake here somewhere, so tell me if I have. Now, I would be a mug not to use equation 1, wouldn't I, to try and work out what a is. It's so much easier. So sub into equation 1. So I've got, yes, have I made a mistake?
No.
Okay.
Good.
Equation 1 is so much easier. So it's a minus 1/2 equals negative 1. And so a is equal to add 1/2 to both sides, a is equal to minus 1/2. Oh, good. I'm glad I got a as a negative number because that fits the graph I've just that I started with. You know, always looking back. Does that fit? Can't look. I think it does. I think it fits.
I don't understand why 1 equal to b.
Yeah, isn't it meant to be?
What have I done?
Oh, you just haven't written the minus 3.
What have I done?
When you've gone to 1 equals 2b,
Just
you just hadn't
You
written
just-
the minus 3
You
above.
just have to,
ah,
you just did in the working out.
is that better?
Yeah.
Rennie, you're my checking king today. Thank you. Is that all good so far? I've got to do the final line, but that's basically it. Y is equal to negative 1/2 x squared. Was it 1? No, was it 1/2? Plus 1/2 x plus 1. I feel like I must have made a mistake, but anyway. Only because in preparing this today, I came up with a simple equation where the numbers would work nicely. But, it doesn't hurt to see a harder example, does it anyway? It's only not nice in that it's fractions instead of whole numbers, but, What do you think? Is that okay? Okay, where to from here then for the rest of the lesson? You've got 20 minutes left, plus homework time, of course. You've got 2 pathways from here. On Google Classroom, I have posted a Desmos activity, and which Lily hasn't started yet, which is a bonus for us. Just continuing just to, should be on the video. On this, look, in terms of getting you to practice the graphing thing, there's only a couple of questions that really require you to do so. The rest of it is kind of a lead up to it, where you have to kind of write an equation which fits the dots, the coloured dots that it says. So if this idea of dilation is sort of causing you heartache and you think it would be worthwhile practicing the skill of determining the right dilation to get a graph fitting dots and stuff, do the Desmos activity, but it is absolutely optional because the first time it gets you to practice, sketching is basically towards the end, like here somewhere. What equation would produce this graph kind of thing. So if you want to you can just skip the Desmos activity if you want. And exercise 3.0 has a whole bunch of these problems where you're given a graph and you need to come up with a function. So honestly, whatever floats your boat. As long as the work's done between now and Thursday, whether you want to do the Desmos activity or not as a lead into it is up to you. Okay, I'll stop the video, then I'll ask if there's any questions.